All right, here we go. Let's see what we can get done. I'm gonna run through the notes. These are actually from the book slides, a little differently than what we did before. But this is a quick chapter, as you guys figured out. I'm gonna go through 2 practice problems. Hopefully that helps with your understanding. So here we go. So we should have the first one. Question, does the ball have a constant velocity? Hopefully you jump up and down and you can scream what? Correct, no. But they go through the long version. So we have a speed. You understand speed is scalar, so it doesn't have a direction. So it's just the number 2 meters per second. So velocity, whoa, shocker, has an actual vector, meaning it's got a direction. That's the huge difference. For circular motion, the magnitude of the ball is changing velocity because the direction is changing. That's where we get the idea the ball is accelerating. So hopefully that makes sense. Again, it's always accelerating towards the center because if you notice, when it comes out to an arc, it'll basically curl back down towards the center, which is what we always wanted to talk about anyway. So, all right. No, the ball doesn't have. Come on. And this is where we talked about how you actually figure out the change in velocity. Just because the change in direction of the movement, you can actually chart it. So the sum of the vectors, vector 1 plus vector 2, on the velocities. They do the same thing with subtraction, and guess what? It's still pointing towards the center. So it's very simple. Now we have our 2 equations that we've talked about. Centrifugal, away from the center, which we very rarely, if ever, use. In fact, your book, I believe, makes the reference never use it, but okay. Centripetal is towards the center. It's what we have to find almost always. If you look at that top arrow, as you pull down, it's got to come towards the center. It's another way to think of it. So our force equals mass times acceleration. Centripetal acceleration is v squared over r. We throw mass in there to get the force, centripetal force. Hopefully that's fairly simple. Again, part of it is always pointed towards the center. Depending on the situation, we'll go through one here, an example, because you've seen one of these, and here you go. So, child of a mass, 12 kilograms, stands on 2 meters from the center. It rotates 8 times per minute. What is the coefficient of friction you're going to need to keep this kid sliding off? You kind of did this in your bookwork, so here's another version of it. So basically we have to set centripetal force equal to static friction. Look at that, centripetal force, static friction. Then we throw in, they use this difference between Fs max and Fs. Static friction is static friction. Static is non-moving friction. So that's the highest amount of friction you'll ever have. So going that, and then they decide, oh, looky there, put max on it. Okay, whatever, got it. It's the same idea. So then you substitute in. If you notice, you have mass times velocity squared over your radius equals coefficient of static friction over F of n. And if you take F of n to one more level, they make F of n equal to mass times gravity. Duh, that makes sense. Mass times gravity in this case. So they change it to mass times gravity. Now if you notice, mass is on both sides. You cancel it out, make it a little bit cleaner. And then they jump in straight into the velocity because you don't have the velocity. You have 8 times per second. So you throw it in, distance divided by time, 8, 2 pi r, again, circumference of a circle. Then you get the velocity is 1.68. Actually, it's a little less. They've rounded up. I don't like it, but I'm going to go with it. And then you plug everything in. And you get a coefficient of 0.144. This is a very simple version of what we did in class. It is a little bit cleaner because this one is asking for the coefficient of friction that you need to find. If you take this idea and go back to the book problem, you'll see it's kind of an easier way to do that. Honestly, the way I did it first time I saw the question. So here we go. This is the one I want to spend a little bit of time on because you will see this question again. You have a small ball at the end of a circle or end of a string being swung at a 30-degree angle. So, take a second, draw it out. If you're reading this or just reviewing, I'm going to draw it out as well because I'm going to solve it massively different than the way they do it, but that's okay. And you'll see why. So again, you've got a radius of 4 meters. The mass is 2 kilograms. Determine the speed of the ball from one side to the next. And then they're going to use F of G, F of T, weight times tension. And this is where I'm going to stop their example, and I'm going to jump over to, hopefully this works out right. Nope. Come on. There it is. So here we go. I'm going to show you the way I did this. So I knew the mass is 2 kilograms. So I knew F of G down here, mass times acceleration due to gravity, 2 times 9.81. F of G has to be 19.62 newtons. That is this bottom. So I know part of this mass here, part of this angle, this going down F of T in the y direction has to be equal to F of G going down, because we're going to split the tension of that string. In my mind, that's a 30-degree angle. That's a 30-degree angle. That means this is a 60-degree angle. So in this case, I can sit there and say, okay, what is the opposite leg of this triangle? Well, I know you have the tension of the string times the opposite sine of 60. That has to equal what's going down, which is 1962 newtons. Divide over the sine of 60. .62 divided by sine of 60. Too many parentheses, don't care. The force in tension of the string is 22.65. I'll carry way too many decimals through. Okay? So in this case, I've got the tension of the string. So this has to be 19.62. This is 22.7. I'm going to just round up for the diagram. Well, then let's find this tension here. We want all the parts, so we take that, since it's adjacent leg times the cosine of 60. We find this is 11.327. Whoops, excuse me. I snuck off the page there for you. So again, I found the force due to gravity coming down. I knew that the gravity down had to equal the upward force of that tension. So I put F of T for this part, set to equal the force of gravity. So F, another way to think of it, F of T in the y direction has to be equal to F of G. And then I found F of T. And then I separated it for this F of T in the x direction. Now, why is that important? Because when we get to it, we will try and find the question. So they want to know centripetal force, F of C, is equal to, and the whole thing is coming back to what is the velocity, right? So F of C, our equation for F of C is mass times velocity squared over the radius, correct? Hopefully. I'm certain you guys can see this on the screen. It would be nice if my ugly mug wasn't there. So now, we know the force is centripetal. What's pushing us out and pulling us in, this has to be 11.32. We know the mass is 2. Velocity squared is what we're looking for. And the radius was 4. So 11.32 times 4 divided by 2, we get 22. Square root of that answer, hopefully, is 4.76. Oops, yeah, 76. Now again, why did I do it this way? I'm going to walk through the whole thing one more time. Because to me, this makes sense. It's always a dangerous statement, but okay, here we go. So I found the force due to gravity because I knew the ball and I knew the gravity was pulling down. Gravity is easy to estimate. I took the mass times gravity, found 19.62. I know there has to be an opposite force in the y direction because they're balanced out. So I set the force of tension in the y has to equal force due to gravity. How do I find the force of tension in that string? The force tension, the whole tension of the string, times the sine of 60, which would give me just the opposite leg. And I found the tension in the string is 22.655. Now, that being said, I had the tension in the string. I had to find the side that was adjacent, so it's the cosine. So 22.65 times the cosine of 60 gives me 11.32. Now if I notice, that angle is the same as this down here. So that's why I set the 11.327, that edge, equal to my force centripetal. Because the string might be pushing us, or the velocity might be pushing us out, the string is pulling us in. So that's where F of C gives us that. Then I'll solve for velocity. I guess I should go ahead and put meters per second. That is one way to solve this problem. Okay? Jump back over here real quick. This is the book's version, and I don't like it because I don't use tangent much. For some folks who love geometry, this will be like, oh, that makes so much sense. So again, we have the ball swinging. Our radius is 4 meters. F of G. This is where I do not like it. They jump straight into an equation where they say tangent of 30 is equal to F of C times F of G. Yes, you can use your tangent to find that angle. 30 degrees, F of C, and then they actually go ahead and cancel the mass out. So you're left with tangent of 30 equals velocity over radius times gravity. And then they go ahead and do the algebra and plug everything in. Again, not fond of this, but they do get the same answer. Velocity equals 4.76. But again, the reason I don't like it is they're using a tangent versus the sine cosine. All right. Maybe that helped, maybe it didn't. A little different problem to see. Oop, keep jumping. Force due to gravity. We've talked about the universal law of gravitation. The idea is the same. Huge G, every object has gravity. Mass 1, mass 2 over the radius, the space between them. Okay? And it is from center to center. Hopefully that makes sense. Hopefully you caught that in the reading. G, they are giving you the gravitational constant. It's on your sheet, so you'll use it if you have to. Most of the time they don't have it in the physics exam, but that's okay. Yes, gravity. So the force applied on an object is the same as that object placing on the satellite. Example, our moon. Our moon has gravity on Earth. It just doesn't move Earth because the moon is bigger. However, if you know anything about tides, the moon does play a portion of our reason we have tides, high tide, low tide. Where the moon is, it actually affects and pulls of water. Very strange, but true. It's kind of fun discussion, but maybe later. Yeah, and gravity acts on the center. So, still have mass times acceleration. Yeah, that always works. Yes, we understand, hopefully, that depending on where you're at on the planet, if you're higher away, example, the gravity at Death Valley is definitely higher than in the Himalayas, just because the radius is so much bigger. Doesn't seem like that much, but when you look at the numbers, it does change gravity very slightly. It's also why physics will often, like the AP physics version, we use 9.8. Because if you really get accurate, 9.81, 9.814, I think 9.8114 is Kansas gravity. I'd have to double check, but anyway, you can actually calculate the true gravity you have by using all the significant digits of G, the mass of the Earth. So it's kind of fun, but anyway. Satellites. We talked about this already. Satellites have to have a speed. In other words, to stay in the current orbit, they have too much speed, they fly off. Woo! They have too little speed, gravity pulls them in. The cool news is, centripetal force, force due to gravity, everything cancels out. So it's like one of your radiuses cancels out, your velocity can be easily solved. This is how you solve for the velocity you need to keep yourself in orbit. And why? Honestly, the satellite doesn't matter how big it is or how much mass it is. When they talk satellites, they're worried about their mass only because they have to build them on Earth and then get them up into orbit. And you're like, well, why don't they just build it in parts and take it up in parts? As funny as the movies are, and they make it seem like, oh, we can just go up and grab the next satellite and lock onto it, it's not that easy. To match orbit, everyone's like, oh, it's just you match that ring, you match the velocity. Yeah, you have to match the velocity in all three directions, X, Y, and Z. They make the movies sound, oh, it's like, oh, it's easy, I'll just put this little... No, it's not. It's the calculations that go behind it take an entire staff. It's hilarious when they do it in the movie. But anyway, I digress. And there you go, satellite mass is irrelevant, cool beans. Time period, we didn't take much time to talk about it. We might talk about it today, because you hit one or two of those problems on your homework, but we'll see what happens. And again, this is just, honestly, it's a plug and play type of equation. You'll be given that equation. Weightlessness, I always laugh because it's not weightless. You're just falling at the same time as all your surroundings. So yeah, in this case, the astronaut, she's basically falling with the shuttle. Like, they're falling at the same speed. If they're not falling at the same speed, it's kind of like you driving down the road. You driving down the road, you have to be going the same speed as your car. If you're not, bad things happen. The only other thing I can tell you about is when a car takes off, that force you feel, that is the force of your body trying to catch up with your surroundings, or in the case of a car, your body trying to catch up to the speed of the car. So, there is a quick overview of Chapter 6. Hopefully it hits what you need, and I will post this hopefully on YouTube better than I did the last time, because what I did 2 days ago vanished into the ether. So hopefully you guys have questions. We'll talk about more in class today. Bye-bye.